today we will talk about that how these monosaccharides, whose examples glucose and fructose we have discussed, they are represented in different conformations. Then we will talk about glycosides, then how the ring size in glycosides is determined and how ultimately the ring size in carbohydrates, particularly monosaccharides, is established. And finally, we will summarize our today's work. We have discussed that D plus glucose is a compound which has got 6 carbons, and the position of these 6 carbons was established that they are present as a straight chain as shown here. Then the carbon number 1 is given to this aldehyde, and then remaining 5 carbons have got 1 hydroxyl each. So, in this structure we found that there are 4 asymmetric carbon atoms, and based on this 16 stereoisomers are possible, and out of these 16 it is one that is representing D plus glucose. This configuration was established by Fischer, and we had got this configuration showing the position of hydroxyls and hydrogen on these carbon atoms. And then this Wagen dash structure was represented by Fischer in a planar way, we call it as a Fischer projection. When this 6 carbon structure was established, then certain new facts were observed at the time, like mutarotation and formation of glycosides. I will talk about glycosides today after the reaction with one molecule of alcohol and so on, and on this basis a cyclic structure for D plus glucose was reported. The question was that which hydroxyl is involved in the ring formation, because if it is a hydroxyl at carbon number 5, if it is involved in the ring formation, we get a 6 membered ring, or if hydroxyls at carbon number 4 is involved, we will have a 5 membered ring, and if it is the hydroxyl at 6 carbon, we will have a 7 membered ring. So, how to establish the ring size, that was a big problem, and that took a very long time in establishing this. But when the ring is formed, we get a new asymmetric carbon atom, which was earlier as aldehyde, and now again 2 more isomers are possible. These isomers are known as anomers, and in the D series of sugars, if this hydroxyl is on the right side, we call them as alpha anomer, as shown here written as alpha form, or if the hydroxyl comes on the left side, then we call them as a beta anomer or beta form. Then D minus fructose has been found ultimately to exist as a 5 membered ring structure, and its 5 membered ring structure is also formed by the cyclization of any hydroxyl from the chain with this carbonyl group, and again 2 anomers are possible when the hydroxyl is written on the right side, because it is a sugar of D series. We call it as a alpha anomer, and its name becomes alpha D minus fructofuranose. And we discussed earlier that if it is a 5 membered ring structure, we name those sugars as furanose, and if it is a 6 membered ring structure, we name those sugars as pyranose. So, these are the 2 anomers for D minus fructose, they are named as alpha D minus fructofuranose and beta D minus fructofuranose. Now, how do we write this ring? That is how we write the cyclic structure in the planar form. There are certain conventions. The first convention is that hydroxyl, which is involved in the ring formation, on whichever side its configuration is established, a ring will be drawn from that side, such as this is representing alpha D plus glucopyranose. So, it is, if in 5 membered ring structure, this hydroxyl will be involved. In 6 membered ring structure, this hydroxyl is involved at the 5th carbon, and in the configuration of D plus glucose, this hydroxyl is on the right side. So, we draw this ring from the right side, and if this hydroxyl is on the right side, this becomes alpha, this belongs to D series, and it is a dextrorotatory compound. So, we represent all these things before the name. Alpha anomer belongs to D series, is dextrorotatory compound, it is glucose, and then it is a ring which is a 6 membered ring. So, we name it as glucopyranose. Then another representation was given, that was the Haworth representation, in which this ring is placed in a horizontal way. Means if it is in this plane and this is the ring formed using hydroxyl and oxygen, this is tilted like this. So, it becomes in a horizontal plane and this right hand upper corner is always given to oxygen. It is drawn like this. So, this end is given to oxygen and this carbon number 1 which was here, that has occupied this position. So, the hydroxyl that was on the right side or hydrogen whatsoever the groups are on the right side, when this ring in this plane is tilted like this, then all those groups which are on the right side will be below the ring. So, this hydroxyl at carbon number 1 is on the right side, at carbon number 2 is also on the right side. So, they are shown below the plane of this ring. This hydroxyl on carbon number 3 is on the left side, it goes above. So, this planar representation is called Haworth representation. This is better than this because it shows all the bonds which are of almost the same length in the form of a hexagonal ring, whereas here it seems as if there is a bent bond between this carbon through oxygen and then bent bond between this oxygen and this carbon. Then further we know that 6 membered ring structures, they exist as a chair and boat form conformations, and chair conformation is most stable. So, these sugars also exist mostly in the chair conformation, and the chair conformation for this anomer of glucose can be drawn like this. And for drawing these chair conformation, we will keep oxygen in this corner. As in the Haworth projection, we have kept the oxygen here, the oxygen will be there, and then this carbon at carbon number 1 is going down to going upward and so on. So, this hydroxyl group in the alpha anomer that goes below the plane occupies here this axial position, and in beta anomer this will be occupying as a left position. In the Haworth position this will be going upward, and in the conformation this will be occupying this equatorial position. So, this way we can represent glucose or any other monosaccharide in different ways. This is a planar cyclic structure, this is the Haworth projection, and this represents the exact conformation for this molecule. Now, as I said that there are certain conventions which are used for drawing the planar cyclic structure for these monosaccharides, and I said one convention is that this ring is drawn from the side on which side the hydroxyl is present, such as here. This is again I am showing alpha D glucopyranose just for comparison. This hydroxyl was on right side, so ring is drawn from the right side. This is beta D minus fructopyranose. You see it is a beta anomer, hydroxyl on the left side. 5-membered ring structure furanose, it is a furan and 5-membered ring structure, so called furanose. It is a levorotatory compound belonging to D series, and in D series hydroxyl on this carbon is on the right side. So, that is why ring is shown from the right side. Whether the compound is levorotatory or beta anomer, it does not affect drawing of the ring. But this one L plus arabinofuranose, again it is a 5-membered ring structure. Now, this sugar arabinose having 5-membered ring structure, so it becomes arabinofuranose, but hydroxyl occupies this position, is on the left side, which is involved in the ring formation. That is why a ring is drawn from the left side. So, if any hydroxyl of the chain is involved for the ring formation, if the ring is drawn from that side, on whichever side the hydroxyl is present in the exact configuration for that compound. If hydroxyl is on the right, ring will be drawn from the right. If hydroxyl is on the left, a ring will be drawn on the left. But the problem comes that if this CH2OH, that is the bottommost hydroxyl group, if this is involved in the ring formation, such as in this is a 6-membered structure for fructose, it is fructopyranose, it is levorotatory but belonging to D series. So, when it is D series, this hydroxyl is on the right, it is a alpha anomer, this hydroxyl is also on the right, but in the ring formation this hydroxyl is involved. Now, here the convention is that if the compound is levorotatory, we will draw the ring from the left side, and if the compound is dextrorotatory, then ring will be drawn from the right side. As this isomer is levorotatory. So, ring is drawn from the left side. Say this is beta D minus fructopyranose. This is another anomer for fructose. A ring is 6 membered, it is a beta anomer. So, this hydroxyl is on the left side, but we have drawn this ring from this side because this is a levorotatory compound. L plus arabinopyranose, a 6 membered ring structure for arabinose. Now, this hydroxyl is involved. Since it is a dextrorotatory isomer, then we draw the ring from right side. So, these are the conventions for drawing the rings when we draw planar cyclic structures. Now, let us talk about the glycosides. We have discussed while discussing the determination of the cyclic structure for glucose, it was found that glucose reacts with one molecule of alcohol and the products formed, they behave like acetals. So, we say that acetal derivatives are formed when a monosaccharide reacts with an alcohol in the presence of an acid catalyst. These were called as glycosides, and on this basis we said that probably these monosaccharides, as far as we are talking about glucose or fructose, they exist as a hemiacetal structure. One of the hydroxyl of the chain adds on to the aldehydic or ketonic group, and we already have the hemiacetal structure because after reaction with one molecule of alcohol, the compounds which are formed, which we are calling them as glycosides, they behave like acetals. Now, whenever a glycoside is formed from a monosaccharide, the other part which is not the monosaccharide part is called aglycone, and the bond formed is called a glycosidic bond. Let us say this is any monosaccharide, say it is 6 membered. This is the anomeric carbon that after the ring formation, now this is hydroxyl group. It reacts with methanol and we have obtained this as methyl glycoside. So, this linkage, the bond between this oxygen and this sugar moiety, this monosaccharide moiety, and then next the oxygen of this alcohol whatsoever it is called glycosidic linkage or glycosidic bond. Now, it is not necessary that it is always a simple alcohol. In nature we get hundreds of compounds which have hydroxyl group. They may be phenolic compounds or alcoholic compounds, and they have got some glucose molecules attached to them by this glycosidic bond, and all such compounds are called glycosides. Here I have taken one naturally occurring compound, glucovanillin, which is obtained from the flowers of a plant, and this on hydrolysis gives glucose and vanillin, a very important compound which is used for vanilla flavor in food added. This is the glycosidic bond here. This is the phenolic group of the vanillin and it is attached to this glucose moiety. So, we call this compound as glucovanillin, and this compound is classified as a glycoside. Glycosides may be formed even between two sugar moieties, two monosaccharides themselves. Say this is one monosaccharide. Hexagonal ring structures obviously are indicating a pyranose ring, but it is not necessary that always monosaccharides have a pyranose structure. They may be 5 membered or 6 membered ring structures. It is just a representation here. Say this is representing one monosaccharide unit and this is its acetal carbon. Acetal carbon means which after reaction is behaving like acetal. Originally it was like aldehyde, and this is another monosaccharide moiety whose hydroxyl at 4th position is acting as alcohol and has joined with this hydroxyl here. So, that is why we call it as acetal carbon. This is the carbon that is using its hydroxyl group, and now this carbon is like hemiacetal because it is having the hydroxyl group here. So, any of the hydroxyl of any monosaccharide may act as alcohol and form the glycosidic bond with any other monosaccharide unit. There is another possibility that this anomeric carbon of the two monosaccharides may form the glycoside bond. So, then in that case what will happen? Both the carbons they will become the acetal carbon. This is shown a sugar moiety in the inverted form. This is the carbon number 1. Means generally, as I said, we draw sugars like this end is given to this oxygen. Now, this sugar is like this, it is inverted like this to show this second molecule, and this anomeric carbon comes on this side and it has formed this glycosidic bond. So, glycosides can be formed by the reaction of monosaccharides with some alcohol, some phenol, any other compound which can provide some hydroxyl group, and this another molecule can be even another monosaccharide. All these compounds are generally grouped as glycosides. Now, how the history went in the determination of ring size of these monosaccharides. In 1893, which we have discussed earlier, Emil Fischer found that glucose reacts with methanol in presence of HCl to give a compound which was named as methyl glucoside. This was obtained by refluxing glucose with methanol in presence of HCl, which behaved like acetal. Then in 1894, Eckenstein was repeating this experiment, and he found that the product that is obtained is not a single compound, it is a mixture of two compounds, and he isolated a second isomer. These were called as the normal glucosides, and the two isomers they were assigned as alpha and beta methyl glucosides. Then in 1913, Fischer was doing some other experiments on glucose, and he could isolate two more methyl glucosides when he prepared this glucoside by dissolving glucose and methanol with 1% HCl and keeping the mixture at 0 degrees Celsius. Earlier the glycosides were obtained by heating the glucose with methanol and HCl. Two more compounds which were different from the earlier glucosides were obtained by keeping the mixture at 0 degrees Celsius. It means glucose gives 4 different methyl glucosides. Now, how to assign these things? So, obviously, it was said that there is difference in the ring size probably, and then again each is alpha and beta ionomer. And problem of the ring size was solved by Haworth and Hurst in 1927, and they reported a 6-membered ring structure or the gamma oxide ring structure for the normal glucosides. I am repeating, normal glucoside we said, which are obtained at high temperature by boiling glucose with methanol and HCl, and a 5-membered ring structure was assigned to gamma oxide ring structure also was assigned to the other glucosides which are obtained at 0 degrees Celsius. Now, a sequence of reaction was used by Haworth and Hurst, and we are going to take that. First, D plus glucose is taken, it is treated with methanol and HCl and it is refluxed. The compound that is obtained, methyl D glucoside. This is treated with dimethyl sulfate in presence of NaOH. Now, what dimethyl sulfate does? It prepares or it gives the methyl ether at all the hydroxyl groups which are there, and we obtained a compound that was named as methyl tetramethyl D glucoside, because it was found that 4 more methyl groups were introduced. Then it is hydrolyzed with HCl. Now, what happens on treatment with HCl? Whichever the acetal bond is formed, there the hydrolysis occurs and we get back the hemiacetal type of structures. So, we got a tetramethyl D glucose. Then it was oxidized with bromine, and what bromine does? It oxidizes the aldehyde group into carboxyl group, and it at about 90 degrees Celsius forms a lactone. Lactones, you know, are the cyclic esters, means the carboxyl group and hydroxyl group of the same chain are involved, and it was then oxidized with nitric acid. One of the products formed was trimethoxyglutaric acid, which is this, a 5-membered dicarboxylic acid having 3 methoxyl groups. This was obtained as one of the product that gave idea about the ring structure, and based on this a 6-membered ring structure was reported. Let us take that ring structure and explain these reactions and then show finally the formation of this product. This is a cyclic 6-membered ring structure for glucose. We have not written the ionomer here, it may be alpha or beta. It is treated with methanol in presence of HCl at reflux temperature, and again we have not shown the anomers here because mixture of both alpha and beta glycoside is obtained. So, here it becomes CHOCH3. It still has 4 hydroxyl groups 1, 2, 3 and then 4th. On treatment with dimethyl sulfate in NaOH, we obtain this tetramethyl derivative. Now, this tetramethyl derivative is now hydrolyzed with HCl when this acetal is converted back into hemiacetal on treatment with HCl, that is we get aldehyde back and which is present as cyclic structure. So, this is CHOH. Now, this is oxidized with bromine. Now, on oxidation with bromine, this aldehyde is oxidized to carboxylic acid and then again it forms the cyclic ester with the same hydroxyl which is free, which was earlier present as hemiacetal, and we obtain this cyclic lactone. This cyclic lactone is now oxidized with nitric acid. What nitric acid will do? This ring opens up and nitric acid will break the carbon chain on either side where the hydroxyl group is there. So, if hydroxyl group is here on this 5th carbon, it may break on this side as well as it will break on this side. So, if the hydroxyl group is at 5th carbon, we will get this 5 carbon dicarboxylic acid, trimethoxyglutaric acid. If the bond is there at this position, that is between this 4th hydroxyl is there, hydroxyl group at carbon number 4 is there, or hydroxyl at carbon number 5 is there. If this bond breaks, then what will happen? We will get a 4 carbon fraction and a 2 carbon fraction. In this compound on cleavage finally, a 5 carbon fraction was obtained along with a 4 carbon fraction. Now, if this is the hydroxyl group involved in the ring formation, that is suppose it is a 5 membered ring structure, then in no case we can get a 5 carbon chain. And suppose it is the hydroxyl of the bottom carbon involved, that is it was a 7 membered ring structure, then we will get a 6 membered dicarboxylic acid along with a 5 carbon compound. Since in this case we obtained a 5 carbon compound along with a 4 carbon compound, so that showed that hydroxyl group is present at this position which is involved in the ring formation. And based on this, a pyranose ring structure or a 6 membered ring structure was proposed for the normal glucoside obtained from this D plus glucose. Let us understand this by drawing the cyclic structures also. This is Haworth projection for the D plus glucopyranose, and here this hydroxyl is shown with this wavy line because we are not specifying the anomeric carbon here, whether it is a alpha anomer or beta anomer. On treatment with methanol gets converted into this acetal, then on treatment with dimethyl sulfate, all these 4 hydroxyls they get methylated and we get methyl, and then specifying the position for this 2, 3, 4, 6 tetramethyl D plus glucopyranoside. This is hydrolyzed with HCl. Now, again this becomes a hemiacetal structure here, but all these 4 methoxyl groups are there. Then this is further oxidized with bromine water. This carbon is oxidized back into aldehyde. Aldehyde is oxidized into acid, and then this acid is cyclized to give this cyclic lactone. We call it as 2, 3, 4, 6 tetra O methyl D glucolactone here. Then this is oxidized with nitric acid. Now, what will happen? This breaks here, this becomes COH and this is OH. This OH is now present on the 5th carbon. This is carbon number 1, 2, 3, 4, this is 5th. So, with nitric acid cleavage can occur either on this side or on this side, and when it occurs on this side only then we get this trimethoxyglutaric acid. So, based on this, a 6 membered ring structure was assigned to normal glucoside which are obtained by refluxing glucose with methanol. Then the other glucoside which are formed at 0 degree Celsius, Haworth used again a similar sequence of reaction for assigning the ring size to them also. This is D plus glucose treated with methanol and HCl at 0 degree Celsius, we get methyl D glucoside. It is further treated with methanol in presence of NaOH, we get a tetramethyl glucoside. Then it is hydrolyzed with HCl we get the tetramethyl D-glucose, oxidation with bromine, then heating at 90 degree we get the lactone, and then oxidation with nitric acid. Here we obtained dimethoxysuccinic acid, are also called as dimethyl tartaric acid, as one of the product, and formation of this product indicated a 5-membered ring structure for these glucosides. This is the structure for this dimethoxysuccinic acid, or we call it as a dimethyl tartaric acid. Showing the planar ring structures, this is a 5-membered ring structure shown. This carbon is now present as hemiacetal form. On treatment with methanol, we get the glycoside here, the acetal type of compounds. Then treated with dimethyl sulfate, all these 4 hydroxyls they get methylated, and we get this tetramethyl derivative. Then this tetramethyl derivative is hydrolyzed with HCl. Now this carbon gets converted into aldehydic carbon and then present as a hemiacetal structure. It is oxidized with bromine. This is oxidized into carboxylic acid, and on heating at 90 degree gets converted into this cyclic lactone, and this lactone is now oxidized with nitric acid, and we get a 4-carbon dicarboxylic acid. Again I am showing here that if it is this type of structure, that is hydroxyl group at carbon number 4 is there, only then the cleavage will occur on this side and this side, and we get a 4-membered compound, 4-carbon compound, and then on this side we will get a 2-carbon compound. We can again see this thing drawing the Haworth projection for this. This shows the D-glucose furanose, alpha or beta ionomer. We are not showing the anomeric carbon with particular isomer. Treated with methanol, this becomes acetal structure, methyl D-glucofuranoside. Then this is treated with dimethyl sulfate. These remaining 4 hydroxyl groups they get methylated. We get methyl 2,3,5,6 tetramethyl D-glucofuranoside. Then this is hydrolyzed with HCl. Now this is converted back into the hemiacetal structure. This becomes OH, and we have now 2,3,5,6 tetramethyl D-glucose. This is oxidized with bromine water. This aldehyde is oxidized to carboxylic acid and then forms this cyclic lactone, and then this lactone when oxidized with nitric acid, this will open up here. It is this 4th carbon that will get the hydroxyl group, and cleavage may occur on this side or on this side. So, if it occurs here, we will get 2 fractions of 3 carbon each, and if the cleavage occurs here, we get a 4 carbon dicarboxylic acid and a 2 carbon fraction, and based on this, these glucosides which are formed at 0 degree Celsius were assigned a 5-membered ring structure. So, using this sequence of reactions, ring size could be established for glucosides, but there was no direct method available for establishing ring size for the monosaccharides themselves, whether they exist as 5-membered ring structure or 6-membered ring structure. Then the another method for determining the ring size was used that involves the periodic acid. Periodic acid oxidizes the compounds in a very specific way. It cleaves across the carbon-carbon bond, and only those bonds are cleaved where both the carbons have oxygen function. Like in this compound, both the carbon have got hydroxyl group. One molecule of periodic acid is used for the cleavage of one carbon-carbon bond, and wherever the bond breaks, each of the carbon gets one hydroxyl. So, what happens when this bond breaks in the compound? This carbon gets one more hydroxyl. So, 2 hydroxyl eliminate a water molecule and it get converted into carbonyl, and this carbon had one alkyl group and one hydrogen. So, from here we get one aldehyde. On this side it has been shown like this, that this carbon had 2 alkyl groups, one hydroxyl, it gets another hydroxyl, and 2 hydroxyls eliminate water and we get a ketone. Suppose the 2 carbons do not have the hydroxyl groups which are on adjacent carbon, then no reaction will occur, as in this case. Hydroxyl is here and hydroxyl is here, but this carbon has got no oxygen function. So, then this periodic acid is not able to cleave the carbon-carbon bond here. Similarly, if this oxygen function is present like ether, as in this case CH2OCH3, and the neighboring carbon has got hydroxyl, but still this carbon-carbon bond cannot be cleaved by periodic acid. Let us take another example here. Say this compound, now each of these 3 carbons shown here have got one hydroxyl. So, it can be cleaved here and it can be cleaved here also. Since it is being cleaved at 2 places, 2 molecules of pyridic acid will be used. Then when cleavage occurs here, this carbon will get one hydroxyl, will eliminate water, has got one hydrogen and one alkyl. So, will be converted ultimately into aldehyde. From this side, this carbon has got 2 alkyl groups, will get one more hydroxyl like this, eliminates water molecule, is converted into ketone. But this middle carbon gets one hydroxyl on cleavage on this side and one hydroxyl when cleaved from this side. So, basically 3 hydroxyls and eliminates water molecule and gets converted into a molecule of formic acid. So, very specific type of products are formed and only specific bonds are cleaved by pyridic acid, and it was used for determining the ring size in different monosaccharides. Say if it is glyceraldehyde, if it is open chain structure as shown here, it can be cleaved here because this carbon has got oxygen function which is not like ether, it is C double bond O. It will get one hydroxyl, will be converted into formic acid. This lower carbon has got one hydroxyl, will get one more hydroxyl and will eliminate water, will be converted into formaldehyde. This middle carbon will get one hydroxyl each from both the sides and ultimately will be converted into formic acid. So, this chain will be cleaved to give 2 molecules of formic acid and 1 molecule of formaldehyde. Similarly, if 5 carbon say sugar is there, CH2OH, CHOH, CHOH, CHOH and CHO, when it is cleaved, it uses up 4 molecules of pyridic acid because 4 carbon carbon bonds are cleaved and ultimately we get 4 molecules of formic acid and 1 molecule of formaldehyde. Actually, this bottom carbon CH2OH is converted into formaldehyde, all others will get hydroxyl from both the sides, will be converted into formic acid, and this was already as C double bond O, will be converted into formic acid. So, these were used for determining the ring size of sugars, but since the whole of the carbon chain gets cleaved, again the idea about the ring size of the simple monosaccharides could not be ascertained, and again this method was applied to glucosides or glycosides obtained from the monosaccharides, such as this is the glucoside, methyl glucoside. This is treated with pyridic acid. It was found that this normal glucoside, which was earlier assigned a 6 membered ring structure, consumes 2 molecules of pyridic acid, gets cleaved at these 2 positions because here are the carbon with hydroxyl groups, at other positions no free hydroxyl groups are there. This carbon will be converted ultimately into formic acid because we will get hydroxyl from both the sides. This carbon will be converted into aldehyde and this is converted into aldehyde, and it was found that 1 molecule of formic acid and a dialdehyde is obtained. Then finally, this structure for this dialdehyde was ascertained by oxidation. These aldehydes are oxidized by bromine to carboxyl group, and on treatment with strontium carbonate they form the strontium salt. This strontium salt was now hydrolyzed. Now, this acetal type of structure will be hydrolyzed. This will be converted back into OH and then it is further oxidized with bromine water. This hemisteral bond gets cleaved. This becomes COH. This is converted back into COH on treatment with acid. Here from here we will get COH. So, we will get a dicarboxylic acid, that is oxalic acid, and a carboxylic acid with a 3 carbon atom in the chain, and these structures are actually established by finally establishing the compounds which are formed on this sequence of structure. So, normal glucoside was again given a 6 membered ring structure. The same sequence were used for the 5 membered glucoside which were obtained at 0 degree Celsius. It was found that these glucosides also consume 2 molecules of pyridic acid, and it shows that cleavage can occur at 2 different positions. These are the 2 neighboring carbons having hydroxyl each, and here are the 2 neighboring carbon having hydroxyl each. When this is cleaved here, this carbon and this carbon both are converted into aldehyde. When it is cleaved here, this carbon separates as formaldehyde and this carbon is also converted into this aldehyde. So, we obtained a trialdehyde whose structure was also established, and based on this finally it was confirmed that the glucoside which are obtained from D plus glucose at 0 degree Celsius have a furanose structure or 5 membered ring structure, and those obtained on refluxing with methanol and HCl have got 6 membered ring structure. But actually the ring size in glucose itself was established somewhere in 1950, when we have the instruments like X-ray crystallography and other NMR etc. All those techniques were used, and finally we say that the glucose in cyclic structure, it does exist. In the solid state, mainly a 6 membered ring structures they contribute, with a very small amount of open chain structure and the 5 membered ring structures. But when it is dissolved, they all reach to a equilibrium, and there we have the equilibrium of all the 5 forms. And when we do any chemical reaction, whichsoever form is consumed, that is, its amount is reduced, and other forms are ultimately converted into that form to establish the equilibrium, and finally a corresponding product is obtained. So, now a final structure about the glucose as well as other monosaccharides is there. They exist as 5 membered ring structure as well as 6 membered ring structure. Depending upon the nature of that monosaccharide, 5 or 6 membered may have the maximum ratio. As in case of glucose, the 6 membered ring structure is there in the larger amount. Fructose, the 5 membered ring structure in larger amount. So, this is about the ring size in monosaccharides. In our next session, we will talk about the disaccharides or polysaccharides which are obtained by combination of these monosaccharides. So, let us briefly revise that today we discussed that how the final configuration of glucose was established, then it was found to have a ring structure on the basis of certain reaction, and then the how do we represent these monosaccharides. We discussed that what are glucosides, and then we discussed the sequence of reactions which are used in determination of ring size in glycosides.